Welcome to Curium. As part of Tool 1, you are expected to be able to determine the enthalpy change associated with a reaction using the calorimetry technique. Note that the concept of calorimetry could be assessed in Paper 1A or Paper 2, but the experimental aspect of this is most likely to be assessed in Paper 1B. Before we begin, there are some key concepts that will be helpful for you to understand. What is an exothermic reaction? What is specific heat capacity? What is the enthalpy change of reaction? The formula Q is equal to mc delta T, which is given to you in the data booklet, and the formula delta H is equal to minus Q over N, which is not given to you in the data booklet. The concept of combustion, what it is, and also HL students would be expected to be able to calculate the enthalpy of combustion. Note that in the previous syllabus, enthalpy of combustion was also assessed at SL level, so if you're searching past exam questions, you're likely to see that also assessed there. Let's begin by revising the concept of calorimetry. So, calorimetry is simply just a technique that's used to measure the enthalpy change that's associated with a particular reaction. And in chemistry, we focus on two main types. There's direct calorimetry, and we use this when the temperature change of the surroundings can be measured directly because your reaction happens in solution. If you haven't already watched the video on direct calorimetry, I'd recommend that you start there before you start looking at indirect calorimetry. The focus of this video will be on indirect calorimetry, and we use this only when the temperature change of the surroundings can't be measured directly. For indirect calorimetry, your setup is maximized in order to make sure that all of the energy that's released by a particular reaction is absorbed by something else. Typically, you'll have a substance combusting. This is often maybe an alcohol. So the substance will be in a piece of equipment called a spirit burner, and the substance, which is a liquid, will get soaked up by a wick, sort of like a candle wick, and that's what you set alight. What will happen is all of the energy that's released from that flame should be absorbed by the water, which is in a calorimeter. That means that we want to make sure that the calorimeter isn't preventing any of the heat getting into the water. So we pick something like a copper can. That's because it's a really good conductor. It has a really low specific heat capacity, which means that all of the energy that's released by the flame should go directly into the water and isn't being absorbed by the calorimeter. What we do is measure the temperature change of the water using a thermometer. Note that for this, it wouldn't be possible to directly measure the enthalpy of combustion otherwise. Think about how we measure enthalpy changes. It's using the formula Q is equal to mc delta T. You can't really just stick a thermometer into a flame and measure the temperature change of that. So this is the only way that you could actually get data that measures how much energy is released when something burns, is if we transfer that energy to something else. Let's look at an example of an experiment where this would happen. So maybe you're burning an alcoholic ethanol. It reacts with oxygen, forms CO2 and H2O. So you put your ethanol in the spirit burner, and what we assume is that all of the energy that's released when that ethanol burns goes into the water. So all of the heat energy from combustion goes into the water and causes the temperature of the water to rise. Let's look at an example of data that you would get from this. So all of the heat energy that's released from the flame we've identified is gained by the water and causes the temperature of the water to rise. What we can assume is that the temperature change in the water is a direct function of the energy that's released from the combustion. So let's measure, or let's process this data to determine how much energy is gained by the water. We can do that using Q is equal to mc delta T. We know the mass of the water because we'll have measured the volume of water that we put into the calorimeter in the beginning. We know the specific heat capacity of the water because we can read that from the data booklet. And we know the delta T, the change in temperature, because we'll have measured it here. If we're able to calculate then the Q value of the water, what we can assume is that however much energy was gained by the water is equal to the heat that was lost by the combustion. Often they might then ask you to process this further. So maybe now that we know the total heat that was released by the combustion, they might ask you to make that a molar value, particularly at HL level. So for example, if it took half a mole to produce a particular energy change for the delta H, you would multiply that by 2, and then it will give you the molar value. They may also give you the value in grams. So for example, it could be that they told you 3 grams of fuel was required to produce a particular delta H. In that situation, you would turn the grams into moles and then do the same thing again. Figure out if this many moles was required to produce a particular enthalpy change, what would be the enthalpy change associated with 1 mole. Let's look at an example of the data you would get from an experiment like this. If you're told that 2 moles of ethanol causes the temperature of 30 centimeters cubed of water to increase by 15 degrees. So you're told your delta T, your change in temperature. You're given a particular volume of water, but I can easily convert that to a mass because I know the density of water is 1 gram per centimeters cubed. That means that for every centimeters cubed of water I have that equivalent number in grams, which means that I also have a mass of 30 grams of water. The specific heat capacity value is given to you in the data booklet. Note that that value quotes 4.18 joules per gram per Kelvin, but the temperature that you're given here is in Celsius. However, it doesn't make a difference because here we're dealing with change in temperature. And every 1 degree Celsius is equal to 1 degree Kelvin. They just have different starting points. So if you have, for example, 0 degrees Celsius, we know that that's equal to 273 Kelvin. If that temperature increases to 15 degrees Celsius, that means that your Kelvin value is also going to increase to 288 Kelvin. It's a difference of 15. So plus 15 in each case, the delta T, the temperature change, is the same. So I have a value for M, mass, I have a value for C, specific heat capacity, and I have a delta T. So I can input that into the formula which is given to you in the data booklet. That works out at 1,881 joules. That means that if the water gained 1,881 joules, that had to have come from the combusting fuel, which released 1,881 joules. So you just need to change the sign because whatever was gained here was lost here. The question told you that it required 2 moles of ethanol to do that. So the 2 moles of ethanol released this much energy. That means that 1 mole of ethanol would release half that value. So your value for your enthalpy of combustion would be minus 940.5 joules. Note how important the minus is here. In an exam, if you don't put in that minus, automatically you'll be losing a mark. There are some major assumptions that we make when we do this calculation. What we're assuming is that all of the energy that's released by the spirit burner is gained by the water. We assume that nothing is going to the surroundings. In reality, that's not true. Energy is being lost all the way along. Before it even enters the water, it's being lost after it enters the water as well. Often, in order to prevent the heat loss to the surroundings, what people will add are draft shields, which are essentially sort of like heat-proof mats that they put up in a box around the experimental setup. This is to minimize the heat that's actually being lost to the surroundings. We also assume that all of the energy is being released by the combusting flame and it's entering the water, and we assume it's staying there. And in reality, that's not the case. As soon as heat will enter that water, heat will also start to leave. So what you may also do is add a polystyrene lid to the top of the copper calorimeter. Remember that a polystyrene lid is a really good insulator, so it will really prevent that heat loss. We also assume that all of the heat that's being lost here goes straight into here and that the calorimeter isn't absorbing any of it. Whereas in reality, it probably is. Although we've picked a material with a particularly low specific heat capacity, meaning that the amount of energy it will absorb is minimal, it is still absorbing some, so it's worth noting that. Another key assumption we make in our calculations is the fact that the density of the water and the specific heat capacity of the water are the same as that of pure water. The values for density and specific heat capacity are both quoted for you in the data booklet, and these are what we use in our calculations. However, this wasn't confirmed. We didn't confirm that all that's there is pure water, and often in experiments, they might actually use tap water. And if that's mentioned in the experimental setup, then for sure that you know that this assumption will have had an impact on the final Q value that you calculate. When you do your experiment and you calculate a Q value, so the energy that's gained by the water, and now you have linked it and you understand that it's minus the delta H for the alcohol, you will likely get a value that's much less than what's called a theoretical value or a literature value. So this experiment will have been done many times by people in other labs with better equipment, and they will calculate a value and share it with the international scientific community, and that will be quoted as the theoretical or literature value. When they do the experiment, They will ensure that they have complete combustion happening only. That means that there's excess oxygen present, and this is important because complete combustion releases more energy than incomplete combustion would. A reminder that incomplete combustion happens when your oxygen is not in excess and what's formed is carbon and water. Note that if you've added draft shields, while this is good for preventing heat loss to the surroundings, it does inhibit the reaction in terms of oxygen availability. It inhibits the ventilation. And if not enough oxygen is able to get in, that means that the reaction that will be happening will be incomplete combustion, which releases less energy than complete combustion. So if your setup is most likely a mixture of some complete combustion and some incomplete combustion, overall, the energy released from your reaction is going to be less than the reaction that you'll be comparing it to in a theoretical value. You'll also notice that in your experiment, you'll have a small amount of black powder or solid formed on the bottom of your calorimeter. That's because of the carbon that's formed. So for sure, you know that incomplete combustion is definitely happening. It may be helpful now to just compare quickly indirect and direct calorimetry, because I know that students often get these mixed up. Direct calorimetry can only be used if the reaction that is happening happens in a solution. So for example, when you added zinc to a copper sulfate solution. Because the temperature change that you're measuring is of that solution, you want to make sure that none of the heat leaves what you're measuring. And so you make sure that your calorimeter is an insulator. And when you calculate Q is equal to MC delta T, that's directly for the reaction that you're trying to measure. This is not the same in an indirect calorimetry technique. We do this when the reaction can't or won't happen in solution, so for example, something like combustion. We make sure that because we want to measure the energy gained by this, that we want all of the energy to leave the fuel and be gained there. We don't want any of it to be absorbed by the copper calorimeter. Hence, we make sure that the calorimeter is a conductor, something that will pass on the heat. When you do your calculation, you remember that because we're measuring the temperature of the water, and the delta T that we put in would be for the water, that means that obviously it has to be the mass and the specific heat capacity for the water as well. And anything that's gained by the water was what was lost by your spirit burner. So Q is equal to minus delta H. An example of a paper 1B exam question, which would be considered easy medium level of difficulty, is on the screen now. This question is worth 8 marks in total, so if you want to pause the video and set yourself a timer for 12 minutes, and you can rejoin us as we discuss it later. The question tells you that the enthalpy of combustion of methanol was being determined experimentally in a school lab, and they used a spirit burner containing methanol, which was weighed and used to heat water in the test tube as illustrated below. This is simply a manipulation of the experimental setup that we already saw earlier in the video. The following data was recorded, and you're given data around mass of burner and methanol initially and finally. There's a mass of water in the test tube, and then an initial and final temperature of water. The first question asks you to calculate the amount in moles of methanol which was being burned. You were from the question told an initial and final mass, and the difference in those mass values was the amount of methanol which was required to heat the water. If you take the final from the initial and work out your mass and convert that into a number of moles by figuring out the molar mass of the alcohol methanol, that works out at 0.0163 moles, and that calculation is worth 2 marks. The second part of the question asks you to calculate the heat which is being absorbed in kilojoules by the water. You were given an initial and final temperature, so the difference between these two is the temperature change, or the delta T. Note that although they give you the temperature in degrees Celsius, because we're dealing with a change in temperature, the degrees Celsius change and the Kelvin change is the same, because 1 degree Celsius is equal to 1 degree Kelvin. Remember, they just start at a different baseline. Using the formula Q is equal to MC delta T, which is given to you in the data booklet, I can input the mass of water from the test tube multiplied by the specific heat capacity and by the temperature change. That works out at 410 joules. Remember, the question asked you to quote your value in kilojoules, so that is 0.41 kilojoules. Remember from the first part of this question, it required 0.0163 moles in order to produce that temperature change. So if 0.0163 moles was required to produce 0.41 kilojoules, how much would 1 mole produce? And that works out at being negative 25 kilojoules per mole. Note that if you quote that as a positive value, they're going to deduct a mark for that, so be careful with the signs in these calculations. The last question tells you that the data booklet value for that enthalpy of combustion of methanol is actually negative 726, quite different from the value that you just got in part 3. It asks you to suggest why that value might be different from the value that you've calculated. And these are all of the assumptions that we discussed already. Not all of the heat produced actually transferred to the water. There was some heat lost to the surroundings of the environment. And note that it's not enough to just say heat loss, you have to say where it's lost to. So it goes to the surroundings or the environment. There may also have been some incomplete combustion happening. The last one, which we didn't discuss, it isn't as easily understood or as common in the mark schemes, is the fact that in your combustion equations, water should be formed as vaporized water, H2O as a gas, whereas maybe in this instant, H2O is being formed as a liquid. That would have a different enthalpy change because energy would have to be required in order to convert that liquid into a gas. So overall, your enthalpy of combustion would be a little bit lower, the one that you measure. Another example of a paper 1B question which would be considered difficult is on the screen now. This question is worth 3 marks. So again, if you want to pause the video and set yourself a timer of 4.5 minutes, and you can rejoin us in a minute when we discuss the answer. The question tells you that a student is carrying out an experiment to determine the energy value of 100 grams of a particular food product by burning some of it. So they only burned 5 grams. And they measured the heat produced by transferring that heat to water in a glass beaker. So it's quite similar to the setups that we had already, except instead of using a copper calorimeter, now they're using a glass beaker. Remember that the reason that we chose a copper calorimeter was because it had a low specific heat capacity, which meant that of the energy that was being transferred from whatever was being combusted to the water, very little of that energy would have to be absorbed by the calorimeter to bring it to the same temperature. That's not the case with glass. We can see that glass has quite a high specific heat capacity. So I can no longer just ignore this in my calculations. Of the data that was recorded, you're given the mass of water that was heated, and you will calculate the difference in temperature from the initial and the final temperature of the water. This other data is also going to be relevant. We know that we'll already use this in the Q is equal to MC delta T formula the same way that we have done in other calculations. But we're also going to want to factor in now the specific heat capacity of the glass beaker too. So if we work out Q is equal to MC delta T of the water, same as normal, our calculation looks no different than the one we just discussed. The challenge here is making sure that you don't just ignore the fact that the glass is also absorbing some of the energy to raise its temperature by the same amount. So those two values combined is the total Q value of what was gained by the setup here, which means that if we know what was gained here, we can more accurately determine what was lost by the thing that was being combusted. That works out at being 4,777 joules. And remember that it also asked you to calculate it for 100 grams of the food product, and all you burned was 5 grams. So if 5 grams produces 4,777 joules, how much would 100 grams produce? And this works out at being 95.5 kilojoules. This question is certainly challenging, but note how they're quite generous with the errors carried forward and also in the marks that they will allow, even if you didn't actually factor in anything to do with the glass. You can still get 2 out of the 3 marks, and that's because at the time they realised that most candidates didn't actually use all of the data given. So when it comes to a question like this, even if you're not sure of exactly what to do, it's certainly worth making a couple of attempts and using data that you have, and you may end up getting most of the marks.